We now know that applying a function to a random variable gives another random variable with its own PMF. So by now, a PMF is something we can build and transform. But a PMF is a lot of information, a whole table of values and probabilities. Very often, all we really want is one number, an average. This chapter is about the operator that produces such numbers, expectation. In this video, we define the expected value of a discrete random variable, compute it for a die roll and for a coin tossed until heads, and see what kind of object it really is. Here's a PMF. It answers every question about its random variable, the probability of each value of any set of values. Complete, but detailed. Suppose we want a single number that summarizes where this distribution sits. The natural candidate is a weighted average. Take each value x, weight it by its mass p sub x of x, and add everything up. That sum is the expected value of x, written e of x, and it is also called the mean. Each value contributes in proportion to how likely it is. One caveat: for ranges with infinitely many values, the sum must converge absolutely. Otherwise, we simply say the expected value does not exist. And notice what kind of object this is. The expected value is not a function of the outcomes. It is computed from the PMF alone. Two random variables with the same PMF have exactly the same mean, no matter how different their experiments are. Let's compute one. Roll a fair die once, and let x be the number of dots on the top face. The PMF is flat. Each of the 6 values carries mass 1/6, so the expected value is 1 times 1/6 plus 2 times 1/6, and so on up to 6, that is 21 over 6, which is 3.5, 3.5. Notice the die can never show that value. The mean is a balance point of the distribution, not necessarily a value the random variable can take. Now an infinite one. Toss a fair coin until the first head appears, and let x count the tosses. We met this random variable before. Its range is 1, 2, 3, and on forever, and its PMF halves at every step. The probability of needing k tosses is 1 over 2 to the k. The expected value is the sum of k over 2 to the k for k from 1 to infinity. Infinitely many terms, yet the series converges, and it converges to exactly 2. Watch the partial sums, 1/2, then 1.5, creeping up and settling at 2. On average, it takes 2 tosses to see the first head, an infinite amount of detail condensed into one clean number. Step back and look at what expectation does. In goes a PMF, a complete detailed description of a random variable. Out comes a single scalar, its mean. That is the trade. We give up detail and gain a concise, meaningful summary of overall behavior. And this trade is the template for everything in this chapter. The key idea to carry forward: the expected value is the probability-weighted sum of the values, one number that summarizes the whole PMF. Coming up next, we push functions through the expectation and meet the two summaries that dominate practice, the mean and the variance.